have the planet here, and you have, no, my bad, you have a star here, and you have a planet here, and it's going around the star in whatever orbit. And say for now we don't know it is a circular or an elliptical orbit, though those would be the best educated guesses, of course. And what you do is you pick an x direction and you translate the system in that x direction. It's like, do the equations of motion change? When you translate the entire system, the equations of motion would not change. It's like, is the spatial symmetry of the universe, right? The laws of physics are the same whether you are here or there. So the equations of motion would not change. What that would mean is that since the system is spatially, translationally symmetric, here we have linear momentum has to be conserved. Not exactly linear momentum. It's not exactly linear momentum. It's really conjugate momentum. Momentum conjugate to this x coordinate that we have. Now, in that case, in this particular case, it will be the linear momentum of the planet plus that of the star combined. In this particular case, which is, well, a case simple enough. Yes. So in this case, it has to be that of the linear momentum of the star plus that of the planet, both combined in this case. So it has to be conserved. Now, if the planet moves around the, well, it moves around, it moves around this star, and it then in that particular case, the star has to also move, and it needs to have, say, a direction such that, and a magnitude such that the total linear momentum has to be constant. Though the momentum of the planet individually need not be constant, because as the planet comes, say it comes closer to, well, in general case it comes closer to the star. In that case, it experiences greater gravitational attraction. So obviously the linear momentum of them individually need not be constant. So what we can say is that their sum is only that the thing that is constant, and maybe they individually vary such that their sum remains a constant. So it's like, what orbit do you have for that? It's an elliptical orbit. Why exactly an elliptical orbit? Well, I think we could work out the mathematics and prove that it is the elliptical orbit only that conserves linear momentum in this particular case. In fact, we could do the same for the y and the z axis, and we could say that the momentum along those directions should also be constant. In fact, we could work out, we could see that if we turn the system around, then the equations of motion still do not change. So the system is spatially, orientationally symmetric. So the angular momentum has to be constant. It's like angular momentum about what direction? We could say angular momentum around what direction?